All right, this is going to be our video for the walkthrough of the assignment titled Even More Chain Rule. Now that we've gotten through all of the different types of functions that we can take derivatives of, this will just kind of be about 20 extra practice problems that require the chain rule and using all those different derivatives. So this first one, we've got y equals the tangent of u, where u is equal to 4x squared, right? It's a function within a function, which is what tells us we have to use the chain rule. So the derivative here should be dy du times du dx. The derivative of tangent is secant squared, and the derivative of 4x squared using the power rule is just 8x. So when we multiply these two things together, we should get dy dx is equal to 8x times secant squared of u, where u is 4x squared. For this one, sine 3x cosine 2x, we'll first recognize that this is a product rule problem, right? We have u times v. So it's u dv plus v du to find the derivative. So we'll do that. We'll say that dy dx is equal to our first function, sine of 3x, times the derivative of v. And if we need to, we can do some work off to the side for that. V is the cosine of a function. We'll call it w, where w is 2x. So dv dw should be negative sine w, and dw dx should be 2. So the derivative of the cosine 2x portion of that, using the chain rule, is negative 2 sine of w, or negative 2 sine of 2x. Then we'll add to that v, which is cosine 2x, and we'll multiply that by the derivative of u, right? And u is equal to the sine of a function, we'll call it z, where z is equal to 3x. So our derivative should be cosine z times 3, or 3 cosine of 3x. And so that is our derivative using the product rule that we had to use the chain rule twice within it. This answer would be fine. I would probably write it with the negative 2 all the way out in front. In fact, I'd probably just throw that sign with it. Negative 2 sine 2x sine 3x plus 3 cosine 2x cosine 3x. And that's a good enough answer. For e to the x squared minus 5x plus 1, we're just going to use the chain rule. Y is equal to e to the u, where u is x squared minus 5x plus 1. So dy du should be e to the u, and du dx, using the power rule, should just be 2x minus 5. Right? Remember that the derivative of e to the u is just e to the u. Right? So nothing changes there. Dy dx will just be that 2x minus 5 times our e to the u, or e to the x squared minus 5x plus 1. For number 4 here, we've got 2 to the cosine x. So we have a rule for 2 to the u. Right, so we'll write out this using the chain rule. The derivative of 2 to the u is just 2 to the u times the natural log of 2. And then du dx is just negative sine of x. So we should be able to come up with our final derivative here. Dy dx is just going to be equal to the two of those things multiplied together. 2 to the u, or 2 to the cosine x, times the natural log of 2 times negative sine of x. Here we've got y equals the natural log of 3x squared plus 1. So that's like y equals the natural log of u, where u is equal to 3x squared plus 1. So our derivative of natural log is just 1 over the function. So we have dy du is 1 over u. And then du dx, which is 6x. So we'll just multiply these two things together and get dy dx is equal to 6x over u, or 6x over 3x squared plus 1. For number 6 here, we've got log base 2 of a function, right? Y equals log base 2 of sine x. So this is log base 2 of u, where u is equal to the sine of x. So we'll just use our rule for log base a of u, right? Dy du should be 1 over u times the natural log of that base, right? So times the natural log of 2. And then du dx should just be the derivative of sine, which we should know to be cosine. When we multiply these two things together, we'll get dy dx is equal to cosine of x over the sine of x times the natural log of 2. Well, cosine x over sine of x is just cotangent x, so we have cotangent x over the natural log of 2. And cosine x over sine x ln 2 would be fine as well. Normally, I like to rewrite those in terms of a singular trig function if we can. All right, for number 7 here, we've got an inverse trig function, right? We have y equals the inverse sine of u, where u is equal to x cubed. So we'll just use our rule for inverse sine of u that we should have memorized. It's 1 over root 1 minus u squared. If you don't have that one memorized, you're going to need to. And then we have du dx, which is just 3x squared. And so we'll multiply these two things together to get our dy dx. It's 3x squared over root 1 minus u squared. Well, if we have x cubed as u and we square it, that's x to the 6th if you multiply the exponents. So 3x squared over root 1 minus x to the 6th. All right, for number 8 here, we've got two things going on. We've got a sine of x squared, so the sine of a function, but then we're also cubing that. So the outermost thing that's going on is the cubed. So we have y equals u cubed, where u is equal to the sine of x squared. And so in order to differentiate both parts of this, the first part's easy enough, right? The dy du is just 3u squared. But to find du dx, that's a function within a function again. So we can rewrite this as u is equal to sine v, where v is equal to x squared. And so to find du dx, we need to find du dv, which is cosine v. And we need to find dv dx, which is 2x using the power rule, and multiply those together. So we now have three things that need to be multiplied together here to get our final answer. We have a 3 right here, and we have the 2x here, so that's going to be a 6x. And then we have a u squared, so that'll be sine squared of x squared, right, because u was the sine of x squared. And then we have cosine of v, which is just the cosine of x squared. All right, for number 9 here, we have 3x squared plus 3 to the power of 7. So this is y is equal to u to the 7th power, where u is equal to 3x squared plus 3. So it's a chain rule problem, but it's a chain rule problem in which all we have to do is use the power rule, right? dy du is 7u to the 6th, and du dx is just 6x. So if we multiply those two things together to get dy dx, 7 times 6x ought to be 42x. And then we're just left with our u, which was 3x squared plus 3, all raised to the power of 6. For number 10 here, this one's going to get a little bit more complicated because it's a product of two functions, right? It's a product of x squared and tangent squared of x squared. So we're going to use the product rule to begin with. Right, so dy dx should be, and we'll write out the product rule, u dv plus v du. So dy dx is x squared, and then times the derivative of v. So over here onto the side, we're going to find out what the derivative of v is. V is the tangent squared of x squared. So, well, if we think about that, that's a function, tangent of x squared, being squared. So we'll call that w squared, where w is the tangent of x squared. So to find dv dw, that's just 2w. But to find dw dx, well, we're going to have to use the chain rule. Right? This is w equals tangent of z, where z is equal to x squared. So we'll get a secant squared z, right, from our tangent z, and we'll get a 2x from our z. And so now we're going to have to multiply all of those things together, right? This 2w, this secant squared z, and this 2x. So that's going to give us a 4 with the 2 times the 2. And it's also going to give us an x, right? And then it's also going to give us a w, and our w is tangent of x squared. And it's also going to give us a secant squared of z, right? And so that's a secant squared of x squared. Right? So quite a bit going on there. Right? It's the product rule, but it's the chain rule within the chain rule to find one of those derivatives. And then be careful here not to forget that that's only the first half of the product rule. That's just our u dv. So then we need to add to that v du. Right? The du is just the derivative of x squared, so that's 2x. And then we have the tangent squared of x squared as our v. And we can rewrite this probably a little bit nicer here. Let's rewrite this as 4x cubed tangent of x squared secant squared of x squared plus 2x tangent squared of x squared. And that's a good enough final answer. If you want to factor the 2x and a tangent x squared out of it, you're welcome to do that, but I don't necessarily need you to do that extra factoring unless you just want to. So that's number 10. That's half of the assignment. Let's take a look at number 11. We've got a quotient of two functions this time. We've got the natural log of x cubed minus 1 divided by x. So we'll treat this like u over v, and we'll use v du minus u dv all over v squared. Right? We'll use our quotient rule to find the derivative of this quotient of two functions. So we start off with v, which is just x. In fact, let's actually write dy dx here is equal to v, that's the x, and then du. Well, to find du, we have to think about u as the natural log of some function. We'll call it w, where w is x cubed minus 1. So to find the derivative of u, to put into our quotient rule, we need to do du dw, which is 1 over w, and we need to do dw dx, which is 3x squared. So we end up with a 3x squared over u, where u is x cubed minus 1. All right, and so that's our v du. And then we need to subtract from that our u, which is natural log of x cubed minus 1, times our dv. Well, the derivative of x is just 1, so I don't need to bother to write that. And then that's all divided by v squared. Since v is x, that's x squared. And you know, this is a complex fraction, so it'd probably be better if we simplified this down. let's start off with just writing this as 3x cubed over x cubed minus 1 minus our natural log of x cubed minus 1 all over x squared. And we can see that in order to get a common denominator here, all we really need to do is we need to multiply by x cubed minus 1 here, and we'll do that here as well, x cubed minus 1. And then we've got a common denominator, so we can drop that all down and say that this is equal to 3x cubed minus the natural log of x cubed minus 1 times x cubed minus 1, all divided by x squared times x cubed minus 1. All right, for number 12, we have e to the sine of x squared. Well, e to the sine of x squared is y equals e to the u, where u is the sine of x squared. And so we should immediately recognize that as we want to find the derivative of the sine of x squared, that's the sine of a function that we'll call v, and we'll write v equals x squared, and it's a chain rule within the chain rule problem. So dy du is e to the u, and then to find du dx, we do du dv, which is cosine v, and multiply that by dv dx, which is 2x. So when we multiply all of these things together, we just end up with our dy dx of e to the sine of x squared, right, our original function that we started with, times our cosine of v, which is our cosine of x squared, and then times 2x. For number 13, we have an inverse trig function again. So we have y equals the inverse tangent of u, where u is equal to x to the 4th power. So the derivative of inverse tangent of u is a rule we should have memorized. It's 1 over 1 plus u squared. And then du dx should just be 4x cubed. So we just multiply those two things together to get our dy dx. It should be 4x cubed over 1 plus x to the 4th squared. And we'll remember that x to the 4th squared, you just multiply the exponents there since it's a power to a power. We end up with x to the 8th. All right, here we've got another inverse cosine function, or an inverse trig function. But that's not actually the most global thing happening in this problem. What we've actually got is we've got y equals a function being squared, right, where u is equal to the inverse cosine of x plus 5. And so as we go through and do this, we realize that we're going to have to use the chain rule a second time. This is u equals the inverse cosine of v, where v is x plus 5. So we're going to have 3 pieces here to multiply together to get our final answer. First of all, we're going to have dy du, which is just 2u. And then we're going to have du dv, which we should have that rule memorized. It's the opposite of 1 over the square root of 1 minus v squared. And then we should have dv dx, which in this case is really convenient. It's just 1, so we can kind of ignore that as we go in and try and write out our final answer. So dy dx, again, is the product of those 3 things. So dy dx should be a negative out in front with a 2u, where u is the inverse cosine of x plus 5 in our numerator. And then we're multiplying that by the dv dx, which is 1, so we can ignore it. And then in the denominator, we have the square root of 1 minus v squared. Well, v is x plus 5 squared. So it'd be nice to expand that out, since then we can have some terms that we can combine together. So we'll end up with negative, and then still 2 inverse cosine of x plus 5. And then in the denominator, we've got a negative of the x plus 5 squared. So that's going to give us a negative x squared, right? Because x plus 5 squared gives us an x squared. It would normally give us a plus 10x, so we'll have a minus 10x. And it would give us a plus 25, so we're going to have a minus 25. And I guess maybe it's helpful if I write this out. Right? This is what x plus 5 squared is. Right? And so we're getting the negative x squared, the negative 10x, and the negative 25 as I distribute that minus sign through. But the negative 25 plus the 1 should just give us a minus 24. And that should be our final simplified answer there for number 14. All right, for number 15 here, we've again got a function x cubed minus secant x that's being raised to the third power. So this is y equals u cubed, where u is x cubed minus the secant of x. So dy du should equal 3u squared, and du dx should equal x cubed minus the secant of x. Oh, that's not the derivative. That's just the function. Du dx should equal the 3x squared minus secant x tangent x, right? I don't know why I didn't take the derivative there. So now when we multiply these two things together to get our dy dx, we have 3 times u, which is x cubed minus secant x, being raised to the second power. And then we multiply it by 3x squared minus secant x times tangent x. And that should be our final answer for number 15. So for number 16, we've got another inverse trig function. It's the inverse secant of the sine of x. So this is y equals the inverse secant of u, where u is the sine of x. So dy du, we should know that rule. It's 1 over the absolute value of u times the square root of u squared minus 1. And then du dx should just be the cosine of x. So then we can just multiply these two things together. And so we end up with dy dx is cosine x over the absolute value of u, so that'd be the absolute value of sine of x, and then times the square root of u squared, so sine squared x minus 1. And so you might be tempted to try and turn the sine squared x minus 1 into a cosine squared x, but it's actually negative cosine squared x, which if we try to do that, we can see that we're going to have a little bit of an issue here. So we're just going to leave our answer just like this. This is fine. For number 17 here, we've got 3 to the x minus the sine of 2x. Right? And so for that, we're just going to use the rule for 3 to the u, where u is equal to x minus the sine of 2x. So to find the derivative here, we'll do dy du is just equal to 3 to the u, natural log 3, because that's the rule for that. And then the u equals x minus the sine of 2x, well, du dx is just going to be 1 minus the derivative of sine 2x. Well, we'll do that off to the side here. Sine of 2x is like the sine of b, where b is 2x. So that should give us cosine b times 2, right? Or 2 cosine 2x. So our final answer here should be dy dx is equal to 3 to the x minus sine 2x times the natural log of 3 times 1 minus 2 cosine 2x. All right, number 18 here, we've got e to the x being squared. So we could think about this as a function being squared, But we could also think about it, and I think the easier way to think about it is just to say this is the same as e to the 2x, right? Just multiply the exponents. So now we have y equals e to the u, where u is equal to 2x. Okay? And so if we do that with our derivative here, with our chain rule, we just get dy du equals e to the u, and du dx is equal to 2, right? And so that's going to just give us dy dx is equal to 2e to the u, or 2e to the 2x. And if we didn't think about that, and you just did y equals u squared, where u is equal to e to the x, well, the derivative of that would be dy du, which is 2u, and du dx, which is e to the x, right? And so what we would have to do is we'd have to just multiply those two things together. We'd get dy dx, which is then equal to 2 times u, so 2e to the x, times e to the x. Well, if we have the same basis of e, we can add the exponents. X plus x is 2x. So whichever way you look at it, you'll get the same answer. I think it's easier to deal with the exponent first and put it in simpler form, but it's up to you. They both work. All right, for number 19, our second to last one here, we've got y equals log base 2 of ln x. So that's y equals log base 2 of u, where u is ln of x. So we will just use our chain rule, take our derivative of each one separately. dy du should be using the rule 1 over u times the natural log of 2. And then du dx should just be 1 over x. So our final answer here, when we multiply those two things together, should be 1 over x times ln x, right, because that's u, times ln 2. And our last one here, this is just y equals e to the u, where u is 4x minus 8 times the natural log of x. So dy du, again, we know that rule, it's just e to the u. And du dx, we'll use the power rule on 4x to get 4. And on 8 ln x, we'll just do minus 8 over x. And so when we multiply those two things together to get dy dx, our final answer is just e to the 4x minus 8 ln x times 4 minus 8 over x. And that is it for these derivatives on our even more chain rule assignment, kind of running the gamut of all of the different rules that we've learned. You got to have all those rules memorized for the test. So that's it.